And with this, we are going to transition to the FlameCommander, and Martin from Netflix is going to tell us a story how they use Cloud Profiler to get data at Netflix scale.
Well, good afternoon, everyone, or morning, depending on the time the video is actually played. I'm not sure yet. So thanks for joining me virtually here today. My name is Martin. I'm a performance engineer at Netflix, and my goal here today is to share a bit about FlameCommander, our internal cloud profiler. If you attended last year's Perfect Scale conference, here in the Bay Area, or seen the videos online, this is an extended version of my FlameScope talk. Starting with a bit of context on how this started for those who are not here. So if you're a performance engineer, you probably had to troubleshoot issues like the one on this chart before. You might have been CPU utilization spikes or response time spikes. It doesn't matter. But something that was intermittent, might be every 15 minutes or so, like this case, or something that was very fast and you could only see a blip off. For example, for CPU issues, we would usually capture a sample CPU profile with Linux perf at 99 Hz and visualize it as a flame graph. So if you're not familiar with flame graphs, it's a form of visualization for profile software. Been around for a while. And the way you read is the x-axis is not the passage of time like you would see on Chrome's flame charts, but the stat population. So how frequent that stack is. The wider the bar, the more frequent that stack frame is. So the y-axis is the actual stack. The problem with using this approach was that it was tricky to capture the issue on a 1 minute flame graph, which is usually the duration we use, as the onset of it kept fluctuating. And capturing a longer flame graph didn't help much either, as the issue was kind of washed in the normal workload of that server. Flame graphs are great. We use flame graphs extensively at Netflix, but they don't have a time dimension, which makes troubleshooting this kind of issue a bit more tricky. So we created a secondary visualization to complement flame graphs and add that dimension to our analysis. A subsecond-offset heatmap, which looks a bit like this, a heatmap, but not a regular heatmap like you are used with, where you have a metric frequency over time. You have the time passage on the x-axis and the buckets on the y-axis. On our heatmap, both axes represent time. Each column representing a full second, and each cell represents a fraction of that second. So if we have 10 rows, for example, each pixel or each cell in that heat map represents 100 millis of that profile. It's drawn bottom to top, left to right. The color of each box reflects the number of events that happen within that time window, so that cell. The darker the red, the more events happen. With that secondary visualization, we created FlameScope, sort of a proof of concept of that idea. So once you open a capture profile, like from Perf, the first visualization you would get is the sub-second offset heat map. That's how you visualize the whole profile. You find the interesting bits like blips in high utilization, blocking, different phases, and you zoom in by clicking in the heat map cells. And that takes you to a flame graph of just that small time window. For example, if I have a heat map with 10 rows, each cell representing 100 millis, like I mentioned before, and I select 3 cells, I'm zooming into 300 milliseconds of that whole profile. And that's the flame graph you get. So you can go back and forth between those two visualizations, zooming into different parts of the profile that you find interesting. And that's how you troubleshoot the issues. This new visualization helped us solve that intermittent behavior problem. because now we could capture longer profile and zoom into the interesting bits, like those spikes, for example, and know exactly what was going on. But as we started looking at more profiles with FlameScope, even things we captured in the past, we started seeing interesting patterns in them, things we didn't really notice before or knew about the applications. Things like this, single threads waking up once a second. You see that nice straight line. Two threads, very similar, waking up once a second each, at different intervals. Busy wait threads, this is really common. This thread does about 20 milliseconds of work. Each cell there represents about 20 millis of work, then sleeps for a whole second. As I mentioned, it's a very common pattern, and it results in the wake up of offsets creeping forward each second. We have heavy busy wait threads, where the slope is higher, as it's doing more work per second. In this case, looks about like 4 cells, so 20 millis each. I get about 80 milliseconds, and then sleeping for the whole second again. I have less busy wait threads, where the slope is a bit less, and because it's doing less work per second, probably just a few milliseconds, so it takes a few seconds to fill that 20 millisecond window. Busy wait threads, they wake up every 5 seconds. You have this kind of different line there. You have different CPU utilization levels. This is what you would get if you maxed out all CPUs perfectly. It's all a red thing. A bit more realistic, you have like 50 CPU utilization workloads that composed by short requests, random intervals, and so on and so forth. 25%, 5%. We can see load increasing, where we get this nice shade of things getting darker and darker as time passes. It gets busier and busier. We have variable workloads, sort of a normal 25-ish% workload in the background, and every 30 seconds or so there's a 5 second of heavier work being done, similar to the issue I mentioned before. We have CPU perturbations. Every so often all CPUs max out for a few hundred milliseconds. This is a very common pattern in Java, where the perturbations are caused by garbage collection. So we see those a lot in Java applications. CPU blocking, every so often all CPUs idle for hundreds of milliseconds, blocking on something like I/O, for example. Obviously, things are not always that clear. What we usually see is something more like this. A mix of everything: busy threads, sleeps, blocking behavior, perturbations, load increasing. But with FlameScope, we can now easily find those patterns and better understand what the application is doing. It's a simple visualization, but it allowed us to simplify the process of troubleshooting certain classes of issues and identify these interesting workload patterns that we were not aware of. FlameScope is an open source project. It's on our GitHub page, and you can use it as a standalone tool or use its components in your own profiling application. So feel free to clone it, test it, fork it, send your PRs. We are always open to contributions. As I mentioned, FlameScope helped us a lot, but is more of a showcase of this new visualization than a full-fledged profiling solution. It reads from local disks, so users had to download it. If they're not from the Python world, they had to get Python and learn how to use VM if they're a bit smarter. Get all the dependencies to get it running. If they wanted to build the client application themselves, they had to get the whole React and Webpack environment going, download tons of dependencies, and so on and so forth. And on top of that, they had to know how perf works or any of the other profilers and all the options and how to configure them and what will happen if they change them. They had to solve frame pointer issues and symbol resolution issues, and the list goes on. Let's say this is not the lowest barrier of entry for most engineers, especially if you never had to deal with performance issues before. And the barrier of entry is a really important factor for us. See, we have a small performance engineering team at Netflix, 5 engineers to deal with all sorts of performance issues end-to-end globally for all our users. So we need ways to scale our efforts. And one way of doing that is by creating tools and having more engineers use them. So engineers across Netflix can troubleshoot performance issues without even involving us. With that in mind, we thought, hey, why not have a centralized FlameScope? It's a lot easier for users. FlameScope is already web-based, so we just need a centralized store for the profiles and a sane way for users to find and analyze them. Since we might have thousands of engineers using the tool, and things could get a bit crazy. And while we're at it, why not centralize the whole profile collection too, so we can abstract a lot of the complexities from the profilers and avoid the task of copying profiles around. And that's how FlameCommander was born. A centralized web-based profiling solution. It provides the same heat map to flame graph visualization as FlameScope, but uses a smaller, more efficient binary format than the raw perf output. Since we're loading profiles from the network pretty frequently, it made sense to create something a bit smaller. The format and the parser are open source too, and after the fact, we added them to FlameScope too. FlameCommander also allows capturing profiles from any of our cloud instances at the click of a button. It's a web application too. At a click of a button, you can capture any of the profiles on any of our instances on Amazon, and it stores all capture profiles in a centralized location for analysis. The architecture is pretty simple, and I really don't want to get into too many details since I don't have time for that here. But this is how it looks like, from a high-level perspective. There's a Python backend, there's a front end in React, and once users trigger a profile collection from the client, from the browser, first thing we do is obviously check if that user is actually authorized to do that. We have limits on who can do what and where. We do that with our internal service that takes care of that, called Gandalf. Assuming everything is okay, we generate a few necessary tokens for profile collection, like copying the output of the profilers to Amazon's simple storage service, for example. And we do that by using Amazon Security Token Service, or STS. The new thing to us was using Amazon Systems Manager, or SSM, to execute the profiling script on the instances, on the servers. We upload the profiling scripts to SSM, like where they're kept, version and tightly controlled. We need to know exactly what can be executed where, and we request those scripts to be executed on a specific cloud instance. Each instance has the SSM agent running, and that allows the script to be executed. The instance then downloads whatever it needs to execute the script from, again, Amazon's S3, and executes it, creating the profile. It might be running perf and JMap and doing whatever is necessary to capture that profile. And once it's done doing that, it copies all the outputs back to S3. SSM is aware of the execution status, and it notes once it's done, once the profiling it's done, is completed. And it sends a notification via an SNS and adds a message to an SQS queue. That queue gets read by a Lambda function that processes the raw profiler output, might be perf, into something that can be consumed by the backend, like the binary format I mentioned earlier. It also updates the profile metadata on our relational database RDS. So the backend knows when the profile is ready, it was processed, and can actually be consumed. With that, the user can finally analyze it in the client. The container use case, we have containers too. It's very similar. So we just run a different set of scripts on the hosts, not the containers themselves, that isolate the profiles by container. But that's about it. It works from both full EC2 instances and containers too. There was no large leap here, besides a new visualization and a new profile format, but making the whole process easier made a huge difference. Abstracting all the nasty profiling details, making it work out of the box on a variety of scenarios and with different programming languages, that was the differentiator, making it simple while providing options for more advanced analysis. As soon as we launched that and made that available to internal users, usage just kept growing and growing, faster and faster. A lot more work than we could have dealt with within the team. We had something here. So it made sense to continue investing in FlameCommander. So we started by adding more profilers, things that are common to developers, like heap dumps, Java heap dumps, memory allocation profiles, where you can get number of allocations or the size of allocations of that application during a profiling period. And the nice thing is that those can be nicely visualized by the heatmap and flame graph visualization too. We created different variations of CPU profiles, like with and without inline stacks, for example. We added application level profilers like V8 profiler for Node. We added off CPU profile, so we can analyze where time is being spent waiting while blocked on I/O, locks, timers, paging, which is an actual BPF based tool, by the way. And we are working to add more BPF tools to FlameCommander in the future too. And hopefully a web interface for BPF trace too. We also invested a bit more in analysis options, like different stack parsers for flame graphs, invert merge, for example. That inverts the sample stacks before merging. So leaf frames are at the bottom of the flame graph. It's useful when you want to merge leaf frames. Like package name or module name parsers, where the package hierarchy of leaf frames is used instead of the stacks. It allows us to merge packages instead of stacks. Which is useful in certain cases. Demangle or beautifiers for different languages. You know if you use profiles before that sometimes frame names have different weird characters and information that is not really useful for analysis, and it maybe makes it merging the flame graph frames a bit more difficult. This kind of cleans frame names to make it easier to analyze later. Another option we added was breaking the profiles by process ID or thread ID or CPU when that information was available. In this case, you can see on the screenshot here that we get multiple heat maps by process ID, and we can zoom into each one of those independently. You can see that the first process there, Java, it's using pretty much all CPU, and then something started happening towards the end, so I can just kind of zoom into that part or zoom into that other process to see what that was all about. So a bit more advanced analysis options. Also, with the centralized repository for profiles, it's also easier to do cross-profile analysis. We can get a historical view of profiles, for example. What did my service look like a month ago? Like, was he using less CPU or more? Where was the difference? So I can compare things. Like everything is in the same place. This question, was so common that we created differential flame graphs, as a new visualization to simplify the whole process of profile comparison. Differential flame graphs, are quite new to us, so we're still tweaking it, and there are a few different implementations out there. Our option uses two flame graphs to represent the comparison of the two profiles. Let's call them right now as test and baseline, and you can change those names. Test and baseline now, it kind of makes sense to us. The first flame graph, the one you can see on the left on that screenshot, is the actual differential. It highlights the difference between the two profiles. It's drawn exactly like the test profile, so usually the new one. Same shape and same count of samples, and it uses colors to highlight the difference from baseline. Blue frames mean less samples in that stack frame. Red frames mean more samples in that stack frame. Gray means there's no difference. The second flame graph, the one you can see on the right of the screenshot there, is the elided flame graph, which contains all samples that were present in the baseline flame graph, but not the test flame graph. Remember, the test flame graph is the differential flame graph is drawn as the test flame graph, and the baseline is kind of the everything that vanished. I know it's pretty confusing if you've never seen it before, and it takes a bit of time to explain. We had to write quite a bit of documentation to explain the new visualization to users internally, but it proven to be a very useful tool because you can spot differences very easily, a lot easier than flipping back and forth between two profiles. We are working now on middle out merge of profiles, which allow us to merge frames in the middle of the flame graph. So you essentially get two flame graphs up and down of that middle frame. We are also starting to look into cloud-wide analysis, like aggregate usage of certain library across services. So we have a lot more options to play with right now that we have a centralized tool. One side effect of having this centralized profiler too is that we could provide an API and automate certain tasks like profiling a canary release, for example. If you're not familiar with a canary release, in a nutshell, it means we have this new build of something and it's serving a tiny portion of my users and to test it if it's good or not, alongside with production. While this test is happening, I could automatically capture profiles of what's in production right now and this new build, and I could compare those, maybe try to find regressions. So we can automate all those things now. Another very common use case is alerts. Let's say a service has a CPU usage alert. This alert could trigger a CPU profile in FlameCommander. So when the engineer receives the alert and goes check out what happened, he already has a profile to analyze. Obviously we would have to tweak profiling options so we don't make things even worse, but it helps. It makes things a lot faster. We now have scheduled profile collection too, like an hourly job that takes a CPU profile from a random instance in a cluster. So we can create this historical view that I mentioned. And with that, I want to kind of wrap up this quick, high-level overview of FlameCommander with a few takeaways. We saw a lot of value in trying new visualizations and not sticking to line charts and tables for everything. It just makes finding and explaining performance issues a lot easier. We focus a lot on lowering the barrier of entry, with abstractions and simple tools, especially for those without, performance experience. It made a huge difference in scaling our efforts. A lot more people using the tools saved us a lot of time. Within the team at least. Having a centralized profiling tool gave us a lot more analysis options too, like the cross-profile comparison, historical views that I mentioned. It also helped us with discoverability. Like maybe an engineer went to FlameCommander to generate a heap dump, but ended up finding the memory allocation tool. So having everything in the same place helped with discoverability. Development cycles are a bit faster too now because we can make improvement and have those available to all users within a few minutes. And finally, automation allowed us to do things that wouldn't be possible to do manually, like cloud-wide analysis, for example. Well, I'm not sure if I have much time to answer questions now, but my contact information is there on the last slide, so feel free to reach out, and thank you.
Thank you so much, Martin. It was an amazing talk, especially seeing the visualization and how it actually helps developers to understand the issues was very helpful. So it looks like you already tackled some of the questions about open. But we also have a question from Kartik. Actually, we have a bunch of questions from Kartik. And so the first one is, do the profiles only get pulled based on a user action, or can they occur periodically?
No, we have automated ways of capturing. It might be via trigger of something, an alert or a build or anything like that, and also schedule actions. We have a bunch of services that do collect every hour, every 10 minutes or so in production.
Awesome. Any examples of issues that have been solved with FlameCommander?
Most are internal, but we have quite a few examples. We found a lot of interesting things in Cassandra. We have a very large Cassandra deployment, and they're of FlameCommander. I think they're the heaviest internal users there. But during the talk, I mentioned the cloud-wide profiles, merging a bunch of them, and that's finding issues in libraries is something we're looking into in the future. We have a lot of libraries that are shared by a lot of different services, and even a small gain in those libraries could mean a large gain when you sum everything across all services. So we're looking into that right now, but nothing specific to share now, I guess.
Mm-hmm. And what languages, frameworks does it support?
So it depends on the profiler. So a large portion of our there is Java or Node and a bit of Python. So those are more widely supported. CPU profiles work on basically most things. They work in Node, they work in Go, they work in C, they work in Java, they work in Python. So CPU profiles are pretty straightforward. Memory allocation, they work in Node and Java. Off CPU, I think they also work on pretty much everything. Depends on the stack. You have to try a few different things, but it really depends on the profiles. Keep them to work in Node and Java too. So we try to focus on the languages that are used the most internally, and then we expand according to the time we have.
Awesome. And I guess I have a somewhat related question. Since you are Netflix is extremely known for its adoption of Amazon and contributions. Probably you were one of the reasons why Amazon Web Services became so successful, just because you pretty much created an ecosystem for Amazon to some extent, and showed how it's possible to actually use it to solve all sorts of problems. So I'm wondering if you are working with Amazon, or you have any plans to work with Amazon to integrate some of this technology into their stack, especially now that they have Amazon Cloud Guru technology.
Yeah, and we found it interesting because it came right after we launched the first version. No talks yet, but we have a few people from Amazon internally there. They found it pretty interesting. So something might happen in the future. Let's see. I mean, I don't like the idea. I mentioned that we have FlameScope, which is open source, and the FlameCommander, which is internal so far, and they share a bunch of different things. And eventually, we definitely want to open source as much as we can. The thing is that, as I mentioned in chat, there's a lot of FlameCommanders integrated with Amazon, and it would be a bit more tricky to generalize it. But it all depends. It's possible. It just depends on how much time we get to do that. We love to open source things, as you guys probably seen, and it will be very helpful to get as much contribution from the outside too.
Yeah, thank you so much for contributing so much to open source movement. I think you made a huge difference in the ecosystem for Amazon for sure, and I think even for global ecosystem as well. This is all the time we had for Q&A. Thank you so much again, Martin, for joining us.
Thank you.
I hope to see the open standard, especially now that we've seen some interest from Google, and I hope that we have the same problem, so I hope that we'll be able to collaborate as well.
Yeah, that would be great.
Thank you so much.